panel. All right, so where we left off was looking at question 19.38a. We had all agreed that the route in blue was the best method to do the chemistry. And so now we want to set the whole thing up. So what we're going to do is we're going to start it with our primary alkyl halide, which is 1-iodopropane. And we're going to treat that with triphenylphosphine. Okay, so, and you could write it that way, or you could just put the reaction arrow like this and put triphenylphosphine over the top. Either way is fine. And that is going to make our, let's see, that's going to make our, this is called a phosphonium salt, technically. But anyhow, so now we make our phosphonium salt like this, and now we're going to treat that with butyllithium. So I'll just put BULI, which represents butyllithium. And that's going to make our ylide, or our ylene. I'm going to draw it as the ylene form, since that's what they have drawn in the textbook. And then we're going to treat that with our ketone. And so I'm kind of running out of space here, but we're going to treat this with the ketone, which is butanone, this compound here. And that's going to give us the desired product, which is this compound right there. All right, so that's our Wittig reaction for the first one. For B, I'm going to have to switch over to a blank sheet here. So just give me a second while I erase some of our old work here. So just give me 2 shakes of a lamb's tail. I can get rid of all of our old Beals-Alder work. There we go. All right, so for the second compound, so this is 19.38b, we want to make this compound, so this transalkene. And keep in mind that there's a plane of, or an axis, I should say, of symmetry, right, in this molecule. And so we don't have to make a decision in this case. Either way, we have to cut the molecule this way. And so in terms of our retrosynthesis, it's going to come from benzaldehyde, which is this aldehyde. And then our ylide, or our ylene, is going to come from that as well. So we're going to draw our ylene like that. There we go. So now we have the two. So, of course, this is going to come from triphenylphosphine plus, this would be benzyl bromide that we're going to require. So now we can set the whole thing up. So we're going to start it with benzyl bromide. So that's our phenyl with our methylene. And if you chose iodide or chloride, that's fine too. And we're going to treat that with triphenylphosphine, which is our nucleophile. We do our S, so this is an SN2 reaction, right? Nucleophilic attack, loss of leaving group. And we form our phosphonium salt, right? Because you have a positive charge on the phosphorus, you have a negative charge on the bromine. Remember, like I said before, phosphorus comes under nitrogen in the periodic table. So when it has 4 bonds and no lone pairs, it has a positive charge. And I'm just going to move this bromide out of the way like that because I'll have to draw in one of these protons. Because in the next step, we're going to treat it with butyllithium. So we have the butyllithium ion. And that's going to rip off one of these protons. And this time, let's draw the ylide just for fun. So we'll draw the ylide. So it's going to have a lone pair here. We got a positive charge here, like that. And then this is going to react in our 2+2 cycloaddition with the benzaldehyde. And so when it reacts with the benzaldehyde, so I'll just write benzaldehyde here, that's going to give us our final product, just like that. All right, there you go. That's all there is to it. And if you're wondering about the mechanism, so let me just remove this Beals-Alder work. If you're wondering about the mechanism of the 2+2 cycloaddition, let's go over it one more time, okay? So here's our aldehyde, and remember the same thing would work with a ketone. So remember, this carbon is delta plus, the oxygen is delta negative. And so the negative charge on our ylide is going to want to react there. So let's draw the ylide this way. So we've got our phenyl here, we'll get our negative charge here, and then we have our PPH3 like this. So here's the reaction, right? 2+2. So you're going to get a nucleophilic attack here, and the pi bonds, the pi electrons, excuse me, are going to make a bond between the oxygen and the phosphorus. So then we form our oxyphosphatane. So you could always start by just drawing a four-membered ring where you have an oxygen and a phosphorus next to each other. So we have three phenyl groups attached here. Now I'm just drawing them out, all out explicitly. We have our phenyl here. We have another phenyl here, like this, and then we show the fragmentation. So the fragmentation, we want to form triphenylphosphine oxide and a double bond. And that gives us the two products. That gives us, so let me draw it in blue to be consistent here. That gives us our desired product, this compound, plus it gives us triphenylphosphine oxide. And I told you that this compound is extremely stable and it's the driving force of the reaction. So there's a little review of the Wittig mechanism. All right, there we go. So that covers our Wittig section. And now we're going to get into the last new reaction of the chapter, which is the Baeyer-Villiger oxidation. And this is the same old Bayer. You've probably heard of the Bayer company before. You know, their name is on some over-the-counter drugs and prescription drugs as well. And Bayer and Villiger developed this oxidation, which is a really neat reaction where you can insert, so check this out. You can insert an oxygen atom into an aldehyde or a ketone between the carbon and the neighboring alkyl group. So let's say you have a carbonyl compound like this aldehyde or a ketone. You treat it with a peroxy acid. So remember that this is called a peroxy acid, okay? The Lewis structure is shown right here of a peroxy acid. I'm not going to ask you the mechanism of this reaction. And in fact, this isn't the mechanism that's shown in your textbook. This is the mechanism from the 3rd edition, and he changed it between here and the 4th edition. So I'm never going to ask you this mechanism at all, okay? So I'll write down here, will not ask. There, you saw it directly. You can bring that up in my face and be like, you said you wouldn't ask that mechanism. Okay, so now you might be wondering, okay, well, that's a pretty neat reaction, but what if I have two different R groups, like R prime and R double prime? Well, then where does the oxygen go? Is it just a 50-50 split? The answer is no, okay? So if you did have a cyclic ketone, then you'd end up producing an ester in a cyclic compound. And when we have a cyclic ester, we call that a lactone. I think I've mentioned that to you once before. But going back to the whole idea is if you have two different R groups, right? If you have R prime and R double prime, like where's the oxygen going to go? Is it going to go here or here? And that's based off of something called migratory aptitude, okay? Let me just delete that. Okay, migratory aptitude. And the migratory aptitude of R groups is right here. You must memorize the migratory aptitude, that it goes a proton, so you always get a carboxylic acid if you have an aldehyde. Tertiary, secondary, phenyl are kind of tied. I will not ask you to differentiate between those two, so don't stress about that. A primary and then a methyl. And then it says, so something that I wrote in my notes, okay? Like I said, I don't refer to my notes a ton, but a student asked me one time, that order seems really weird, Mr. Dion, you know, how did that, you know, where does that come from? And so something that I wrote down in my notes from another textbook, a more advanced textbook, it says factors, so listen very carefully, factors that control migratory aptitude are not completely understood. So in fact, the reason why it's in this order, it's not that well understood. Students usually memorize it pretty quickly. They just remember if you have an aldehyde, you're going to get a carboxylic acid, and then it goes tertiary, secondary, primary, and methyl, and then a phenyl is tied with a secondary. All right? So that's the rule. So if we look at this carbon over here, okay, so if we look at these two carbons, let me just label this one here, right? This carbon is attached to two carbons, so this would be secondary. This carbon is attached to three hydrogens, so this is a methyl group. And methyl is the loser of the bunch, it's the last place, and so the oxygen is going to go in between the carbonyl carbon and the carbon that is secondary. And then in the second case, you've got benzaldehyde. Well, hydrogen is the king of the castle. And so again, if you ever have an aldehyde, you end up making a carboxylic acid 100% of the time. So there you go. Again, you must memorize. So right here, memorize. And again, this is called migratory aptitude. All right, so you have to memorize of migratory aptitude. So with that in mind, let's practice our migratory aptitude memorization here. Predict the major product of each of the following reactions. So you can see that these are Baeyer-Villiger reactions. Remember, migratory aptitude goes proton, and then tertiary, and then secondary, which is tied with phenyl. And then we have primary, and methyl is the bottom of the barrel. All right, so let's look at the two carbons here. This carbon, how would you classify this carbon? Going away from the carbonyl, how many carbons is it attached to? It's attached to two carbons going away, right? It's attached to these two carbons, and so you would call it secondary, right? Thanks, Deanna. And this one is only attached to one, so you'd call it primary. Secondary is going to be the winner. So we insert the oxygen on that side. So we draw our carbonyl like this. Our oxygen is going to be over here. Then we put our cyclohexyl group, which is going to look like that. And on the other side, we still have our ethyl group. And then in the next one, what kind of functional group are we going to make in the next one? Because we've got an aldehyde, so we're going to end up making a, starts with C, ends with carboxylic acid. That's exactly right. Good guess. I'm teasing you. Yeah, it's a carboxylic acid. Perfect. There we go. And that's it. There you go. Oh, what's that? There you go, carboxylic acid. So the Baeyer-Villiger reaction. It's one of the, whenever I'm lecturing, I'm always thinking, have I ever done this reaction? I think the Baeyer-Villiger is one of the few things I haven't done. Baeyer-Villiger and ozonolysis, I don't think I've ever done that either. All right, anyhow, so let's get into synthesis strategy. So now that we've covered all these reactions, you start to get overwhelmed by, oh man, we've learned this and that, and this way to make this bond and that bond and every other bond. So, what am I going to do here? Well, one thing you have to do as an organic chemistry student, and I just have to admit this, is you do have to work on your memorization skills. There's no doubt about that. But I've heard people say that the mother of memorization is repetition, right? So you repeat something over and over and over, and like you watch the same movie 100 times, you start to know some of the lines. If you try the same problem 10 times, you start to remember the reactions, right? And so one of the first things you want to do now is really ask yourself about changes in the carbon skeleton. Why? Because we've learned so many different ways to change a carbon skeleton. We've learned Grignard chemistry, we've learned cyanohydrin chemistry, we've learned Wittig chemistry, and others as well. And so that's number one, is there a change in the carbon skeleton? And then also, functional groups, you go back to organic too, you covered alkenes, alkynes, and in this class, you've already covered aromatics, alcohols, aldehydes, ketones. Next chapter, we're going to cover carboxylic acids, esters, nitriles, acid chlorides, acid anhydrides. So we're getting into a lot of different functional groups that we can change around. And so I'm not going to fill in all this, okay? I think that if you're unable to do any of these transformations, you need to take the time to fill this in. There's only so much learning that can be gained by me just yammering on and on and on about you should do this and you should do that and you should do this and you should do that. So what I would like us to do then is to spend some time working on some practice problems as a group, and just bear with me. Before we tackle these practice problems, so this is question 19.40. This is I think the last problem we'll maybe look at today. I wanted to show you that towards the end of the chapter, it covers a little bit about IR and a little bit about NMR of aldehydes and ketones, and a little bit about carbon and everything like that. Anyhow, so I just want to show you that we've covered every single thing on here. So all the blue check marks, plus we've covered thioacetal formation. We covered the Rainey nickel reaction. We also covered this reaction, which is the Wolff-Kishner reduction reaction. We looked at the formation of an alcohol from a ketone. Now, this was covered in chapter 12, but we covered again here. Same thing with Grignard. We covered that in chapter 12. Then reaction 13, we looked at the formation of a cyanohydrin. Reaction 14, we looked at the Wittig reaction. And the last one was the Baeyer-Villiger. So we've covered every single reaction on here from soup to nuts, covered the whole thing. And so with all that in mind, let us go back here, now that we've got some real synthetic prowess. And, the first thing we want to do with question C here is take a look at the carbon skeleton. We're starting with something that's got 7 carbons. and we're making something that has 8 carbons. You know, in terms of retrosynthesis here, if we're making a tertiary alcohol and we have a methyl group on the same carbon, you know, my retrosynthesis would look something like this. I must have this compound, right? Because if I can make this compound, then I can just do methyl magnesium bromide, H3O plus, and I'm done. So then the question becomes, well, how in the hell do you get an oxygen in that position? Can I ask you a question first, though? If I have this starting material, what's the only possible reaction that I can do in the first step of this reaction? First step here. Exactly. Thanks, Audrey. Thanks, Tiana. Perfect. Yes, it has to be a free radical bromination. Yes, everybody is correct on this. And so let me just, I'm going to erase this, okay? The first thing we've got to do is a free radical bromination. So let's start out with our starting material. Like Audrey and Tiana said, we're going to do a bromination here, and we're going to make this compound, right? We're going to brominate in the most substituted position. Now, if anybody has tried this ahead of time, the next thing I'll give you a clue, is going to be an elimination. Would we want to make the Zaitsev alkene or the Hoffman alkene in this case? Because there's 2 possible beta protons, right? There's this beta proton in red, and there's this beta proton in blue. I want to make the more substituted of the 2, right? Which is the Zaitsev product. Exactly. So I want to make this product, right, where I've got the double bond here. And now I'm getting closer, you know, to being able to make the ketone that I wanted to make, right? If I want to put this carbonyl here. But before I do the carbonyl, why did I convert it into an alcohol? And so how would I get from this alkene to this alcohol? Would that be a Markovnikov or an anti-Markovnikov addition of water? Exactly. It would be an anti-Markovnikov. So let's scribble this out. Let's write down the reaction conditions. First step is borane and THF. Borane and THF. That's kind of funny looking there. Step 2 is hydrogen peroxide and sodium hydroxide. Yes. So that's going to give us that secondary alcohol that we want. There we go. And now can we oxidize this to a ketone? Yes. And you can use any method that you want. You can use PCC. You can use the Swern. You could use chromic acid if you feel led to do that. That's fine. You can use Desmartin periodinate. Why don't we choose that for a change? Okay. That's going to give us the ketone that we wanted. And then the last step to get us to the final product, we treat it with methyl magnesium bromide, followed by aqueous acid. And there you have it, folks. Done. Just like that. You've completed the entire synthesis. Now, that's quite a few steps, isn't it? That's a total of what? Let's see here. We got 1. Did I skip a step here? Oh, I didn't put my base down here. So this one would be sodium methoxide. Since it's you want to use an unhindered base. So let's see here. 1, 2, 3, 4, 5, 6, 7 steps. That's quite a few steps. All right. There we go. So for the next one, based on what Audrey said and Tiana said before, the next one you're starting with the exact same starting material. Right? We could just move this box down here. Okay, for the next one, we're starting it with 7 carbons again. And are we increasing the number of carbons? So we have 7 carbons here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going from 7 carbons to 9 carbons. All right. So what we'll do is we'll put kind of a line through that. I know we've only been going for a little bit of time here. We just finished Beer-Villiger, and we finished a little bit of synthesis here. But I'd like to give you some time. I think you should at least try these reactions. I think it's worth it to give it a shot. So even if we just take a 5-minute break, I would like everybody to give these a try, okay? It's very easy to sit back, and I'm not accusing anybody of anything, but there's only so much learning I feel you can do by watching somebody solve the problem, you know? Give it a try, and then we'll come right back and we'll try and solve them together as a group.